Okay, today we're going to be learning about another comparison test. Instead of the direct comparison test, it's called the limit comparison test, because sometimes the direct comparison test will lead you to an inconclusive conclusion. For example, look at this particular series right here, sigma 1 over 2n plus 3. If you decide to use the direct comparison test, I'm going to compare it to 1 over 2n, which is a p-series that diverges. If I compare it to this one, notice you are adding a number to the bottom of the fraction, which makes the bottom bigger, which really means the entire fraction gets smaller. So this would be the conclusion. But this is inconclusive using the direct comparison test, because you cannot say if something diverges, something smaller does not also diverge. Something bigger than that will also diverge as well. So the DCT test on this particular series is inconclusive. This is where the limit comparison test is going to come in. The limit comparison test, you start with the same way. You're going to pick the series that it is similar to. And again, I'm going to pick the series 1 over n, which is a p-series that I know that diverges. Now notice I'm just comparing to 1 over n. If you want to leave the 2 in there as well, 1 over 2n is still a p-series that diverges. That constant multiple does not change that. So what the limit comparison test says is if you take the ratio of the two general terms, so basically you're dividing the two terms, and it doesn't matter which one you divide by which. So I took the original, I'm going to divide it by what I'm comparing it to, and when I divide, it's the same as multiplying by the reciprocal, so I simplified it. This limit is 1/2. Basically, the conclusion is if you take the ratio of the two general terms, if you go back to the note card or this box here, and that limit is any value L where L is finite, so basically it's any number and it's got to be positive, then they will do the same thing. So because this was a p-series that diverged, and when I took the limit of the ratio, I got to a positive real number. This is also going to diverge as well. Okay, let's try a couple examples. Most of the time, you will use LCT and compare it to a p-series, most of the time. And anytime you have a polynomial on the top, polynomial on the bottom, so basically things just raised to powers, like A, like C, you can always use LCT and it will always work. So first thing, determine what you are going to compare it to. So letter A, I'm going to compare it to 1 over 3n squared. Remember, the highest power determines what is happening to that graph in the long term. That's why I disregard the negative 5n and the plus 7. So I'm going to compare it to 1 over 3n squared. You can also compare it to 1 over n squared. It doesn't matter if you keep that 3 or you leave it out. And I know this is a p-series that converges. So the limit comparison test says you take the ratio of the two general terms. I always take the original and divide by what you're comparing it to, but you can go ahead and flip it if you want. And this is the same as multiplying by the reciprocal, so this is really this. If you want to go to this step right away, that's fine. This limit is 1. This is a positive real number, so because this was a p-series that converged, you can also say this converges by the limit comparison test, which I would call LCT. Okay, let's try the same thing with B. Again, I'm going to compare it to, this time I'll just forget about the 4 and I'll just compare it to 1 over square root of n, which is a p-series that diverges. I'm going to take the limit of the original divided by what I'm comparing it to. I'm going to turn it into a multiplication problem right away. Degrees are the same. This limit is going to be 1/2. This is a positive real number. So since I was comparing to something that diverged, I can say this also diverges by LCT again. Okay, let's look at the next one. Again, you're going to take the highest powers on the top and the bottom. So really, when you simplify n squared over 3n to the 4th, this is going to become n squared over, it's going to become 1 over 3n squared. So this is a p-series that converges. So this is what I'm comparing to. I'm going to do the limit of the original divided by or multiplied by the reciprocal of what you're comparing to. I notice that the degree on the top and the bottom is the same, so I do the ratio of the leading coefficient. I get to a positive real number, so I can also say this also converges by LCT. Whatever you're comparing it to, it has the same conclusion, basically. Okay, this last one down here, letter D. Again, you have to take everything on the top, because there's only one term, and then the highest power on the bottom. And if I simplify this, though, this really simplifies to 2 to the n over 4n squared. So this is what you have to compare it to. So now this is not a p-series or a geometric, but I can do the nth term test this on pretty quickly, because I notice when I take the limit of this, I have an exponential on the top, so this limit is infinity, which is not 0, so I can say for sure this diverges by the nth term test. So now I am going to compare the original with what I'm comparing it to. So this is my limit that I'm setting up. Notice degree on the top and the bottom is the same. The 2 to the n's will drop out, so this limit is 1. I get to a positive real number, so I can draw the conclusion that the original will also diverge by LCT. So what you need to show me is you need to show me what you are comparing it to, show me the analysis for that piece, show me the limit of the ratios, and then draw your final conclusion on this original series.